Hello, everyone. So let's get started. And I hope everyone has joined. I think people are still joining in, but we'll get started. First of all, thanks, Kasam, for organizing the event and for having me back again. And you must be having, I think this is the fourth session. So there were three amazing sessions before this, and I'm very positive you guys were there for that. And I do recommend that please stay till the end and check out the other amazing sessions which we have. And right now we're having the fourth one, generating poetry or rhyming poetry or text using LSTM RNNs. So this is what we are doing with Azure Machine Learning, Keras, and TensorFlow. Right. So before we start, uh, let me quickly introduce myself. My name is Shivam Sharma, and I'm Microsoft Azure is something which I'm working on since around 2012. I have around 9 years of experience. 8 of that will be in Azure Cloud. I also work in AWS and in GCP as well. And apart from that, in machine learning, I have been working since last 4 to 5 years. And these days, most of my time goes into either data science or data engineering. And I'm the co-founder at Tech Scalable as well. Apart from this, I give lots and lots of trainings and consulting. That's what we do on a day-to-day job, day-to-day basis as such. Now, in case you want to learn more, next week I am doing another webinar. You can go to the profile link which I have pasted into my in the chat window. You can join me on LinkedIn. You can find more about the webinar we are doing on Azure. So the learning should continue even further. So now let's get started. So what are we doing today? Let me quickly explain that part. Okay, so I don't have any slide deck for you guys. Mostly we will be doing discussion on the whiteboard. And secondly, we will be having code and discussion. That's all we are going to have. No slide deck as such. So there is no death by slide, which I'll go do. Now, whenever you have any questions, so we have around 45 minutes with us. And whenever you have any question, please feel free to ask because I think we have a lot of content for this one session. And having a specific separate Q&A in the end may be very difficult to do. So whenever you have any question, please use the chat window, or you can also let me know whatever doubts you have, right? So let's get started. There are two objectives which we have. The first objective will be that we want to understand what is LSTM, what is RNN, and how do we do text generation with it, right? So there are two objectives as such. Check this out. So text generation, that's one thing. And the second thing which we are going to do will be, we have to use Azure Machine Learning to do that. So now both of them will have multiple concepts as such. So I will do my best to explain all the concepts in the time which I have right now, right? So we will be generating the text, and the text which we have to generate will be poetry as such. So everything should be rhyming and so on and so forth. So I don't promise that we will be able to create an amazing poet, but a mediocre poet or an average poet is something which we can create with the in the session which we have, right? So let me just explain the setup which I have, and then I will tell you about text generation, the steps which we are going to do. And I'll stay to the point. I won't be taking you much into the theory as such. I'll explain what we are doing. We'll see in the code and we'll try to finish it in that sense. So first thing is text generation, poetry. And secondly, and what are we going to use? This will be LSTM as such. We'll talk about why are we not using RNN as such, what is the difference between LSTM and RNN, and what steps are we going to do. And as part of Azure Machine Learning, multiple things will come into picture. So we will only touch base on the things which we really require. For example, the data which we are going to use will be in a storage account. So this is the data set we are going to use. What data set is it? How are we treating it? How are we processing it? All of that, we will check it out. But FYI, data will be in a storage account. Storage account in Azure is a blob storage. It's object storage and it stores huge amount of data, something like that. Now, apart from this, you will also see that I have a compute instance with me. I'm positive you might have done your own research on Azure ML. So this is one compute instance that I have. And in easier words, compute instance is equal to workstation, your cloud workstation, like that, like this. And that's my laptop over here, the one which is shared right now. So I will be connecting to my compute instance and my train.py files will be there. So what are these train.py files doing? All of this I will explain. So this is train.py. But the training will happen in remote instance. So apart from this, we will have a cluster over here. And I'm starting from the middle because I'm assuming you were here since the morning. So you have understood some basics as well. So this is my compute cluster, like that. So all of these terms are in Azure. In Azure Machine Learning, we have these terms. Like for example, this storage account is called as a data store, right? Data store. Data set really means data set. It's like tabular and file data set. Two type of data set can be there. Right now, we are not much concerned about whether we should go for tabular data set or whether we should go for file data set. But like that, we will be just having the data in storage account. And this compute cluster will be a 3 node machine will be there. And I'll confirm that. I'm not sure how much RAM did I give, but I think I have somewhere around I think 148 GB RAM on them, somewhere in that range, 112 GB or something. I'll confirm that in the Azure portal. So that much of RAM will be on each machine. We really don't require that much of RAM because once I trained the model, I realized that the data set is not big enough for having so much of RAM. But anyways, I thought that I'll just put it on that, so it will look a little better, right? So something like this will happen. We will get the data from this location, and that's where the training file will be there. And we are going to have a remote run. And once in just FYI in Azure Machine Learning, once you train your model, let's say that's the model getting trained, you register your model. So model registration means like source control. We register that model so can be deployed in future. So this is register. So that's one step we do. So you will also see me do that in the code. Whenever in the code I have to refer to something, I'll come back to this diagram, right? I'll show you that this is that registration step, like this. Just hang in for a minute. And then once you do this, we will deploy. So next step can be deploy part. So for deployment, you can have ACI, or you can deploy in various locations. Let's say there is a Docker container, a model is deployed in production. So that deployment part is not my concern right now. So what I'm going to do, I'm just gonna download my model, something like this, like this. I think in another session, I'm very positive someone will show you how to do the deployment as well. So we'll just download and we will do the local testing over here. We'll test it out, right? So this is a very high level flow that will look like some deployment, remote training, data set coming from one location, some files coming from here, some new terms here and there, 3 node cluster. And what are we doing? We will generate some poetry. So any question which you have in mind till now, please ask. Let me quickly open the chat window as well. Anything you want me to repeat? Okay, I think no question, then let's continue. Check this out. So this is the overview of the structure or infrastructure which I have. And the model training will take around 40 minutes to happen. So I think I will trigger it, but I will just show you the backup one which I have already created to show you that it ran for 40 minutes. But I'll tell you, we'll do all the steps and we'll just execute and we'll see the trained one, right? That's something we are going to do. Okay, now I'm starting from this text generation part. What steps are there? What details do we need to do? When we work with any sequence model, what extra things needs to be done? What do we do with the poetry? What's the meaning of LSTM? What is RNN and so on and so forth? And Azure Machine Learning, I will just show you in the notebook as such, right? So check this out. Let me just quickly check out. Okay, I thought somebody raised the hand. Okay, now guys, notice this. See, mathematic works with numbers. Mathematic doesn't works with text as such. So just to explain the various steps which we are going to do, please notice this over here. So let's say this is my input data set. And for input data set, I have, just like everyone else does, I think I downloaded a data set from Kaggle. I'll show you the data set as well. I'll show you from which repository I got it and so on and so forth. Let's say this is input data set over here. So the input data set will be text. And if you think about text, there will be some sentences over there. So this is what I'm trying to make as a sentence. Sentences can be of varying sizes. That's one problem we have to think it through. Like some sentences may be smaller, some sentences may be very large and so on and so forth. That may cause issues for us. So the input data set can be having multiple files also, right? Right now, I don't have multiple files with me, but you may have multiple files as well and multiple sentences inside those multiple files over there, right? So how does that one sentence may look like? Imagine this is that small sentence over there, right? So this sentence may look like, let's say, quick brown fox. You have heard that, right? Quick brown fox jumped over the something lazy dog and so on and so forth, like that. So quick brown fox, imagine this is one of the sentence over here. Now, whenever you're working with text, there are, you can say, couple of ways by which you can treat or deal with the sentences or the sequences as such. One of the way by which we deal with it is called as tokenization, which is the simplest type of dealing with text as such. So we will also do tokenization. So you will see that we have done one steps and we have created some tokens over here. We will be using Keras to help us with the tokenization step. Now, what does this tokenization will look like? Once the tokenization has done, is finished, something like this will be created. Let's say quick, brown, fox, right? And so on and so forth. There will be more tokens over here. Hundreds and maybe thousands and maybe and so on and so forth can be there in your data set if you have large enough data. So let's say my quick is 1, this is 2nd, this is 3rd, and so on and so forth. Something like this. So tokens will be created. Now, once the tokens are created, we will be doing one step. That step will be called as convert the sentences into, you can say using the tokens, just convert the sentences as such. So just to explain, so you can say quick brown fox. That may look like, so if I create, I use the token, let's say token to represent that sentence, it will look something like this. Let's say 1, 2, 3. There might be some another sentence might be there, which might look like, let's say 44, 77. Let me put it here. So this sentence is slightly bigger, and these tokens, there's some other token is there. Let's say 2 here. Maybe I have 39 over there, like this. And then there might be another sentence which is even bigger or smaller. So let's say 55, 46, 27, 29. I'm just putting randomly now, not thinking much, and so on and so forth. So this is, so one sentence, this is that sentence which was quick brown fox. And these are other sentences in your documents which you have created with over here. So the problem which you will see is that these sentences will be of varying sizes. That's one thing we have to handle whenever you work with text analytics, or whenever you work with RNN or LSTM or anything to do with text. One of the thing may be there that you have to handle this varying size of sentences. Secondly, one of the unique things about sequence models or text is that there is a context over there. For example, the man is wearing a nice hat, right? So the man is wearing a nice hat. Hat is not wearing a man. So there is a sequence over there. There is a sequence of context which needs to be maintained. If you do not maintain the sequence as such, it will practically the output which will come will be sort of rubbish or gibberish will be there. It will randomly things may get generated. So we have to handle the sequence as well. So how do we do that? A pretty interesting thing we'll be doing. We will be creating sequences out of it. So imagine I take one sentence. We will do this for everything, right? But just to explain on one sentence, after this, I'll recap all of it. Whatever I have explained till now, I'll recap it, right? Don't worry. So let's say this is one sequence over here, right? So we will be creating some sequence on top of it. Now, you might have heard about a thing called as n-gram, right? Whenever we work with the text, n-gram comes into picture. In case you have not heard it before, it basically means, for example, if I say bigram or 2 grams as such, then, and my sentence is quick brown fox, right? Then my 2 grams on top of this will be quick brown, and then I have brown fox like that. So 2 grams like that, two of them together like this. So we will be doing something called as n-gram on top of the sentences which we have created. Once we do this, right, any question till now? Let me know. I think someone is not on mute. If you have any question, let me know. Okay, so let's have a recap before we carry on, right? Before it becomes very difficult. So first thing, we have the input data. Input data will be having multiple type of sentences over there, right? So one of the sentence may be looking like this, quick brown fox. Now, how do we handle it? We will create tokens using the entire data set. Whatever data you have on the entire data set, tokens will be created. Once the tokens are created, tokens will look something like this, right? You have quick brown fox, quick might be 1, brown might be 2, fox might be 3, jumped over the moon, jump might be 4, moon might be 6, and so on and so forth. You may have hundreds and thousands and thousands and thousands of tokens as such. Now using those tokens, the sentences will be, or whatever you see the sentences we have will be converted into a vector format. This is where I have all the tokens which are representing my sentence now. There is no text anymore. There is no string anymore. We have like some you can index of the token over here, like 1, 2, 3, 44, 77, 2, 3, and so on and so forth. Once we have done that, we also have to worry about the sequence in the text. So man wearing the hat is correct, hat wearing the man is wrong. So we have to conserve the sequence as well. How are we going to do that? We will, whatever sentences do we have, we will be creating n-gram sequences on top of it. So how do we do that? Notice this. So imagine I'm just taking one, for example, right now. Let's say this is my one sentence as input. If I create the n-gram sequences on top of it, one couple of them will be looking something like this. So let's say 44, 77. Then I have, I'm just trying to make a structure. You will get it why. So let's say 2. Then my third n-gram is 39 to 77, 44. Similarly, if I take on the last sentence over there, 55, 46. And then the next one can be 55, 46, 27. All the possible sequences are there. And the next one can be 55, 46, 27, 29, and so on and so forth, right? So on all the data, we will be doing this. Once you do that, you will have your data set ready, and this data set will be having all the possible sequences that can come in the data. All possible sequences will be there. One problem which should be very evident from this is that we are having the sequences are of varying sizes. Some of them are bigger, some of them are smaller. The problem will be that we have to when we push this data inside the neural network, that's where we'll get an issue as such. So what do? We will try to create uniformity over there. How can we do that? One of the most common way by which we can do uniformity in the data, either it is text data or maybe it is images or something, is padding, right? So one of the step in the code which we are doing will be padding. So if I apply a pad over here, then padding will look something like this. Just for my, let's say, I'm just adding one more. So I can show you how the padding will look like. So let's say 1, 2, 3. We'll put this padding over here, and then something like that. So this is the input data set will look something like this. So all this will be pre-processing of data and finally converting the text data which we have into a sort of uniform input data. Any question which you have till now? Now padding can be done pre and post. We are doing pre-padding, sorry. Pre-padding means that before the sequence we are putting it. Post will be something like this. Right now we are not doing post. Reason will get clear as soon as we hit the next part where we have to extract the X and Y from it. So think it through till now. What comes to mind? So tokens, sequences, and then padding to make it uniform. This padding will be pre-padding like that before the sequences. Now, once we have done this, next step is which you all are familiar with, right? From here onwards, we have the normal machine learning, which comes into picture apart from just using LSTM. So let me just copy it down and notice this. So this is your input data set now. Now, how do we do any machine learning process, any supervised machine learning process? How do we do that? We have X and Y like that. So if this is my input data set, what I can do, I can extract the X and Y from it. So this will become the X as such, and that's my Y over here. You see this part. All the labels will go into Y over there. So if you want to generate text generation is exactly what we do in sort of, you can say you're doing a prediction right now. You're trying to predict the probability that after this much of text, if somebody says that, let me show you one example. I was using the model which I trained, and this is some of the text which I have generated using that model. I was just doing it just to show you that how does it look and feel like. So imagine now I'll tell you what inputs did I did. So I did the input sailor sail the I think sea also of the land. That was the generated text over there. In the second one, I gave the input. I also have to give some input. Based on that, it predicts the next rhyming word. So I said ups and downs in the wave of, I think wave of something. It predicted the sea the morning was. Away from the precious love of life, it said the rose of Tranley. Not sure what that is. Left my wife and mountain. Somewhere till here I gave the input, and that's the output of the model like that. Some sort of what it thought is rhyming. It's not a very good poet, but mediocre poet. So now, if you check this out, so what are we doing? If you give any input, it's gonna predict the output words for you. So we have X and Y over here created. The problem which we have to face after this point is that if you check out this Y are the labels over here. The problem with Y is that Y is not exactly, you can say we have 77, 77, 39, 46, 27, 29, and so on and so forth. Hundreds and thousands of more labels will be there. If I leave them the way they are, mathematically, they will unnecessarily create more weightage on some particular labels as such. So one thing which we'll do over here is one hot encoding of the labels to make them, or you can say in Keras, we have one utility called as to categorical. That categorical will convert my labels into one hot encoded vector. So you will see that we have done this on this Y. We will do that. Here we will say, we will just say Keras to categorical, and it's Keras.utility something and to categorical. And what it will do will create the one hot encoded vector out of it. So if I just explain what that Y part will look like, something like this will become of it. I'm pretty positive you know what is one hot encoding. If not, then you can just relate with this. So let's say I have 27, 29, so 27, 29, 39, 46, and 77, something like this, right? So what that Y will become? Y will become something like this: 0, 0, 0, 0, 1. So this became that. The one hot encoding of the second will be 0, 0, 0, 1 again. The third one will be 0, 0, 1, 0, 0. And fourth will be 0, 0, 0, 1, 0, and so on and so forth. Let's just fill it up. Okay, this is 1, and this is 0, 0, 0, 0, and that's 0, 1, 0, 0, 0. So this becomes my Y, and that becomes my X. What comes to mind till now? Think it through. So let's have a quick recap of what we have talked about till here, and I'll sort of recap all of it. So check this out. So the first thing which we did is we will be taking the input data set. We will be tokenizing the data set. On the tokens, we will find the sequences as such on all the sentences. Once we have done that, we will put some padding over there. With the padding, we will have uniform input data. Once we do that, we will be we will extract the X and Y from it. This is your training data set, and that's all your labels as such. On the labels, we will do one hot encoding. And once we have done this, we'll get something, the Y will become something like that. So this is X and that is Y now. Now comes the sequence part. Till now is all the data pre-processing. There is no, not much of, you can say, not much of machine learning algorithm as such till this point. It's simply just pre-processing of text. How can we do that? Now, sequence comes into picture. And as we all know that what is machine learning? Machine learning can be, if you just try to understand machine learning, this is, we can say that we have X and Y, or let me say data in the label, and there is a function, and that function will tell you the rules out of it. These are the rules as such. This is normal machine learning, like that. So I can say that that function is just a function of the input data set and data over there. Let's say data and label as such. That's what this function is doing. And we get the rules out of it. Those are machine learning rules. Now, normal machine learning or any classical machine learning, or apart from anything, apart from sequence model, other type of models do not preserve the sequences which are there. Sequence is what we were talking about, that you have a very nice hat doesn't have you, right? So that's a nice sequence. So one example of sequence can be, for example, let's see how many of you recognize this. So let's say 3, 5, 8, 13, 21, 34. So in this is basically you can say Fibonacci sequence is there. So what happens over here? The addition of the previous two is the sum of the. So if I add 2 and 3, it becomes 5. 3 and 5 becomes 8. 5 and 8, 13. 13 and 8, 21. 21 and 13, 34. So there is a sequence which is getting maintained over here. So just to relate to RNN, so what are we doing over here? We have these two input. Let's say 1 and 2. If you add this, it becomes 3, right? But then what happens? We also take the 2 from the previous one. So the 2 is carried forward and then we add it again. And then in the sequence, it becomes 5. But here, the previous output also is carried to the next sequence. So the context is going further. So this is where I have 3. And if I add this, it becomes 8 and it is carried further. So this becomes like this. And then I add it like this. And then it's 5. 5 plus 8 becomes 13. And then what happens? We just take 8 further and add it, and it becomes 21, and so on and so forth. Keeping the same logic in mind, right? We have RNN as such, recurrent neural networks. Now in recurrent neural networks, or in normal machine learning, what do we have in classical machine learning or any machine learning process? We simply have that X, let's say X goes in and there is a Y dash coming out, some output is coming out, right? In recurrent neural network, the output of the previous layer will also go into the next input as such. So this is where I have X1 and this is where I have Y1. So the output of the previous one will go in the next one as such, in the next unit. And this is where I have X2 and this goes into Y2 and so on and so forth, like this. Recurrent neural network. So what I can say is that even so in a very high level, what we can say is that there is some, so whatever X0 was there is some input of X0 getting carried to the when X2 came into picture. So in the same sequence, something got carried over there. Now, this is what happens in RNN. RNNs are, you can say, good in terms of carrying the state, but in if the sequence is little bigger, then RNNs are because it's a probability prediction. So if you predict, let's say you are having a long sequence which you are trying to predict, then there is a diminishing return as such, or you can say that it will not predict the output properly. LSTMs were created further to evolve on top of RNN as such. In LSTM, what happens? We have one extra, you can say, and this is on a very high level, right? If we go a little more deeper, it will. We just need a couple of days to understand it in depth. But on a very high level, what LSTM will have? LSTM will have it will have a cell state. There is a cell state concept. So if I put Y over here, and then this is Fx, and this is X2, and this is where I have Y2 as such. So now I have one more thing, a cell state, this one. So LSTMs are even better in carrying the context further. So this is cell state. It will take the context of the sequence further. It will store the context of the sequence. Now these cell states can be bidirectional. The meaning of that is that sometimes, or let me just put it like this, that um, so for example, if I have a sentence with couple of words as such, then going in the forward direction will definitely have impact, but the reverse of the sequence will also have an impact as such. So quick, let's say you have a nice hat, but if I put it bidirectional, then there is a impact of the hat. If I reverse the sentence that a hat is having nice U and so on and so forth, then that is also going to have an impact as such. So LSTM will have extra cell states, and those cell states can be bidirectional. We don't have to always do it bidirectional, but bidirectional is possible. And this is something which you need to see. How is it performing in your scenario? In the code, I have put it bidirectional. I was trying it out. So I found that bidirectional is giving me better predictions than single directional. So I have placed it in that particular sense. Think it through. We'll go in the code now, and whenever required, we'll come back to this diagram. We'll try to relate till which point have we deployed over there. Just to recap, what are we doing? The main structure remains here. This is the main structure, right? So in the train.py, we will have all the logic as such, all the tokenization, all the sequence creation, all the everything over there. We will have a remote cluster and some storage accounts and some compute instances, compute cluster. All these are machine Azure ML concepts. So let me take you to the to Azure, and I will just show you how does it. What are we going to do? So first of all, now I'm assuming couple of little information. I'm assuming that you guys have understanding of Azure platform, and this is Azure machine learning instance. That's how it looks like. You just click from create and you create it, and you launch the studio after that. Now once you launch it, everything is on the left hand side, which will load in a second. Notebooks, automated ML, designer, dataset, experiment, pipeline, model, and so on and so forth. So what I have done, I have already clicked on the compute and I have created this compute instance. This compute instance is this cloud workstation. I could have used my laptop as well, but over a period of time, the laptop sort of dies using machine learning. If I so many environments are there, so it becomes easy for me to keep the code in compute instance. And in your production also, you're not allowed to keep your code in your laptop as such. So anyways, you will not be able to do it. So this compute instance will be in the cloud, and this part is this part over here. Shivam's workstation is that compute instance. Now inside that, if I click on Jupyter, this opens up. So this is a Jupyter notebook which is installed inside that compute instance. By default, if you create that, it will be there. We don't have to do anything about it. You can select which size you want and other details. So this is the workstation where we will be doing the development. And how did we access it? Over the browser. Apart from this, there is a compute cluster also. So where's the compute cluster? If I go one step back, click on cluster, I have two type of cluster. The second one is actually a GPU cluster. You see this remote compute. This is a GPU cluster. It is having 6 core, 56 GB RAM, and so on and so forth. One NVIDIA Tesla K80. Didn't needed that. So I thought that maybe if needed, because RNN actually takes lot of time. But yesterday when I started developing the webinar content for you, I realized that my data set is not big enough to be run on a GPU instance. So I just have it just in case. Now the second one is the CPU compute, and this is having around somewhere. So so there is if I just click on the nodes over here, I think 3 nodes are there, and nothing is running as such right now. So yeah, maximum nodes will be 2. 0 is minimum nodes. So auto scaling happens. It is automatically able to scale out. And 20 core per node, 140 GB RAM. We really don't require all that, but we have very powerful machines which are possible. So this is this part. You see, there's 3 nodes. So I don't have three, I have two as part of CPU compute over here. We also have other things not really relevant right now. Just if you know it, inference cluster is AKS and attached compute is Databricks. If you are aware of it, otherwise just note it down and you can check it out later on. Okay, so in my compute instance, this is a Jupyter notebook which I have opened as such, right? And let's get started with the code part, and we'll check it out. Now, before I do that, I just want to give the credits where the credits are due. And all this code has been taken from Microsoft's documentation from here and there. And apart from that, I found some pretty interesting repositories on GitHub from these three gentlemen as such. And from these repositories, I got the Azure ML. Most of the code was there of registration and so on and so forth. And the data set and the LSTM reference is coming from Mr. Lawrence. And apart from this, some couple of interesting demos are there on TensorFlow. I'll give you all these links in the chat. You can, if you want, you can also go and read further about things over there, right? So, okay, so that goes in the chat now, and it will go in any second now. Okay, some issue with Teams. I thought I lost internet. Okay, check this out. So now let's get started. So the very first thing so I already have done this. So I'm just step by step walking you through it. Whenever you have any question, let me know. Let me zoom in. So it will be possible for you to have a look at it. So first thing is it doesn't matter you are in cloud or you are on premises, you have to connect to the Azure. So the connection to Azure is the first step which we are doing. And because I'm using compute instance over here, I do not have to log in specifically. But if I was using my laptop, I would have given the configuration file over there, and only after that I would have been able to connect to it. And then it might have asked me for some interactive authentication. It might have asked me for some sort of service principal based authentication, or some sort of authentication mechanism was required. We are in the cloud right now. This notebook is in the cloud, so that's why it didn't ask us for any authentication, just FYI. So we connected to the instance. And what is this AML? That's AML is this AML. That's the one. We just connected to it. Now, okay. So now what we have to do? We actually have to, if you see over here, we have to submit the training file to the remote cluster. So if I have to submit something to the remote cluster, I have to have it locally first. So to have it locally, I'm creating one folder. I will put it inside that. So this is the folder which I just created in the previous, when I ran that, the folder got created, and we'll put a file inside that. Right? This is the lyrics pipeline experiment folder got created. Now, the compute cluster. So let me just show that part to you. Check this out. So how do we create a cluster? So nothing has to be done from the portal. What we could have done, we could have simply given the cluster name over here. Let's say CPU-cluster, and we would have given it, like, if you don't have it, create the cluster. You can select the VM sizes, specify how many nodes you want, and so on and so forth. Just specify all the things and run that. So this cluster is the same one which I have here. So it said that I already found it, so I'm not creating it. I'll use the existing one, this one over here. So this is the remote cluster where we will submit the run in these three nodes. We have two nodes. You can just imagine in the diagram I made three, but actually we have two right now. So as such, found the existing cluster. Now comes the train.py file, or the file where your code will be there, the one which you are going to submit to the cloud. So I'm pretty positive that we all agree that deep learning and everything is having a boost these days, because we get the GPU instances or CPU instances so easily in the cloud. If you have to do all this in your laptop, couple of my laptop really died because of the load which training the models for a couple of days stresses or puts on the laptops as such. So it's good. Now check this out. So I am creating a file over here, but let me do it step by step. So there is one thing which I am taking a shortcut right now. Those who, I'm pretty positive you guys are aware of Azure machine learning, but there are methods which are better than what I'm doing right now to get the data from the data stores. You see this over here. So I have the data over there in the storage account. Let me show you. So if I take you to my resource group, and somewhere I have this storage account, and inside this storage account I already uploaded it. So there is a container. It should be saying data, and inside data I have this data. I have Iris lyrics, songs are there, Irish songs are there as such inside this. That's what my data looks like. I can show you just a look and feel of this. That's how it looks like, the input data. So there are better methods to pass it. What I did, I literally downloaded it locally in the machine as such, but you can parameterize that. You can pass it during the runtime in the parameter. So at when you submit the experiment, I'll show you where you can put that, but that's just FYI. In case you work in Azure, you are correct. That's a better way to do it. And this will also work out right now. So we got the data. Data got downloaded. You can say the URL is there from where I'm pulling the data into my compute instance, and this file is not running right now. This file will be locally created. We have to submit it afterwards. So whatever that URL is there, copy the URL locally into that remote compute. So on this line, what will happen? Data will get downloaded and will get stored here. You can say this is the data like that, right? Or is available for my file to access. That's what will happen in that line over there. Now comes the tokenization part. We have to create the tokens as such. So we will initiate the tokenizer, and this is the tokenizer, and it will pick up that file, it will open it, it will read it, and then it's gonna convert everything into lowercase. Couple of line breaks are there, so it will split from the line breaks. If your data doesn't have line break, you can remove it. So it's gonna create that entire, you can say tokens as such. And now we will have total number of words. Total number of words will have 1 plus. 1 plus, we are putting 1 plus because some of the words might be out of vocabulary. Out of vocabulary means that if we talk with English vocabulary and somebody speaks in German, then German word will be out of vocabulary for us. So if something comes like that, we will just handle it with the help of OOV. That's one standard practice which is done. So this step is over here, the step where we were creating the tokens. You see this part. This will do that for the entire data set. Next will be the sequence creation. So if I take you back, check this out over here, right? Now we will create the sequence. Now sequence will be done for the entire all the sentences which we have. So we are saying that for all the lines which you have in the corpus, simply take the sequences and generate the n-gram using that. This will do that part for us over here. This part, not the padding. Without the padding, the initially which we had 4477 to 4477 and so on and so forth. That part will be done on the entire data set over here. Once we have done this, we have to do the padding as such. Now padding is generally done with the help of the maximum length of the sequence. So if let's say one of my sequence is having the length is maybe let's say 10 over there or maybe 15. So that will become my max length. So in this example, my max length will be 1, 2, 3, 4, 5. So I have 5. The length is over here 5, and it depends which programming language are we counting it, but we have like 5 is the length right now, right? Or you can say 0 to 4 is the length right now. So max length, and what type of padding are we doing? Pre-padding. Why are we doing pre-padding? Because if we do pre-padding, it will be easier for us to extract the labels out of it. We can just say 1 minus, then it will the labels will be extracted. If I do post padding after the sequence padding, then that will be very tricky to pull it out in that scenario. So it becomes easy right now. So this is that part over there. Now you can say the normal ML part. You have X and Y. You create X and you create Y. You can take everything apart from the last into the X data set, and in Y we will only have the labels, and we are converting the labels to categories. That's one step we are doing. So this category conversion is this part over here, where we have the one hot encoding. So that one line will create this one hot encoding for you. This part over here, 2 categories over here, like this. Now comes the the LSTM part, right? So now in LSTM, in Keras, how do we define that? This is how very simple LSTM can be created. So what this LSTM is having, we call them sequential models. So we define it like this: sequential add model.add embedding. So we haven't talked about embedding, but I'll explain that. So the first layer will be embedding. Then there is a bidirectional LSTM with 250 units as such. And then in the end, we have a dense layer where softmax comes into picture. Some learning rate will be there, and we have some loss function as well. Loss function will calculate the model error. We'll see it. So this is normal LSTM looking like. And what is the meaning of this embedding? Now, embedding is something which is pretty long to explain, but I am assuming you have some information into it. And check this out. So, for example, if you represent, so with the help of word embeddings, what do? We represent the words into some sort of vector format, and similar type of vectors or similar type of words will be clubbed together or grouped together. So if these are negative sentences, negative, let's say sentences or words over here, these are my positive words right now. So all negative will be clubbed together, all positive will be clubbed together. This will happen with the help of word embeddings as such. So that one layer of embedding will be there in the starting. Now 1000 means the dimension, like the output dimension as such. And softmax is just softmax, and there is a loss function cross entropy. And we are just going to fit it here. This is where the model training will happen. We can do right now 100 epochs will be there. You can increase the number of epochs. It will train for a longer time, but you may have poor results if you beyond that point in time. It depends on your data also. How much data will you have? Now to see the loss function, how is it performing? You want to plot it, obviously. So this is one small, you can say with matplotlib, you can just plot it out. But the issue which you have to understand is that this training will happen remotely, not locally. It is going to happen in the remote cluster. So if I train it over there, then I have to log all the information. So how do I log it? In Azure Machine Learning, we have these standard mechanisms. You can say run.log. And if you say run.log, you actually have to start the log as well. Let me quickly see if I, okay, I'll show that to you. We have to start the logging mechanism as well. Now, once that is done, let me try to do it a little fast. So, just 1 second. Okay, now the save model. So once the model has been trained, you have to save it somewhere. So what are we going to do? The model which is trained over there, we are going to save it into the cloud itself. We don't have to locally save it anywhere. It will get saved into the cloud. So the model is we are creating one folder called as output folder, and we will simply save it over there. And once it is saved, we will have the path and so on and so forth. So this will basically complete your the run which you are having will get completed. What's the meaning of this run? When you submit the code to the cloud, you can say that in the experiment, it creates a run, and that run will be having, you can say some IDs will be there and so on and so forth. So we actually have to start the run first. And this is where we will just say run.get context. And just to explain what is this step, when you submit this run, you see this run is getting submitted. It will create some identifiers of it, like run ID will be there and so on and so forth. So something like this. And we want to log all the data inside that. So let me just import all the correct files, and I will initiate this run, and I'll just take you back to the already deployed model. So we'll see how does it look and feel like. So the file got created. And one last part over here, check this out. And this is how we submit in Azure. So check this out. So whenever you are doing any run, imagine it needs environment also. For example, right now I have the dependency on matplotlib. I also want pandas to be there. I want, let's say, pip install request TensorFlow 2.4 needs to be installed. So I can create environment in the cloud. What this environment will look like. So in this diagram, if I take you here, you see this yellow part, which I have. This yellow part will be a Docker container over there. And inside this Docker container, all the dependencies will be will be here. So this is where we have TensorFlow. This is where we have Python. This is where we have NumPy. This is where we have all the things deployed. So in Azure ML, how do we do that? We just say, let's say Docker enabled, create environment. What dependencies? Specify that. Are they conda dependencies or pip dependency? And so on and so forth. And simply create the correct file. So let me just take the file from here. Otherwise, it will throw me error in the next line. So that's the file as such. Give me a second. Let me copy the correct code. So I have in my secondary screen all of this already done. I'll just take you to that now, and we will simply have a look at that one. How do we sort of do it? I'll just submit the run over here, right? So now this is the environment creation. This is how we specify all the details into one file. Like what all do we need? We need the script which will run, where will it run, what environment is there, and then in which experiment do you want to run it? And you just simply run it like that. So you will notice that it will start doing a submit of the run. And to check it out, you can go back to your Azure portal. And in the Azure portal, simply click on experiment. And you will see that in this one, a run will start now in experiment. And it got queued. So yeah, so I think it got queued. It will. So why it got queued? Because the cluster is coming up. You see this cluster. There is an auto termination on the cluster, which I have put because it's a big cluster, like 60 seconds of auto termination. So if nobody is using it, it should automatically terminate. So first the cluster will come up, then the run will submit, model will train, we will register it, and we will start using it. From this point onwards, this is the one which I have already trained over here, and that's the one I was using till now. So this run from here will take approximately, if I just somewhere around 40 minutes, it will take 35 minutes as such on that cluster for this to run. Once you run it, simply you can download the best model. So if I zoom in over here, the model which I saved before, the Irish lyrics model, that model is having multiple versions. And those versions will be in Azure Machine Learning. If I go to the model section, it will be registered here. You see this, all these versions are there. I think I was submitting it multiple times to check out all the bugs as such. And this is where I have 13 versions of the same model right now over there. And one of them is getting trained right now. Then, so from this point onwards, you have to deploy it somewhere. You can store it, or you may want to deploy that in production or in maybe in a staging environment, or just want to check it out. What are we going to do? We are downloading it. Once we have downloaded it, we are simply going to do a scoring with it. This is the part which I was showing you before, where whatever data you specify, it will predict the next words in that sequence. So if my seed statement or my input data is, they will take me back to, and I'm saying that LSTM generate next 8 words, right? So something like this. So back to the town of the bridge of to me today, and so on and so forth. So something like this. So now I'll be very honest. It's not a proper poet, but it's sort of creates something which we have done for 1,000 line of text which I have given to it. If you want to outperform this model, you have to basically get more data. That's one thing that will really help. Secondly, we may help do some hyperparameter tuning with the LSTM. There we have the word embeddings are there, and we have the output dimensions. That's one thing which we can play with. Secondly, learning rate can be played with. We can try different units of LSTM as well. I think I have around 250 or 150 something. You can have more or less and check it with it. So, and apart from it, so for example, all of this is generated by that model only. So if you have any input ideas, you can think it through, because the sequence will be generated based on the input which we have to give. So it also depends on what input do we give. One thing which I have noticed is, I'll show you two things. First of all, if I increase the number of words over there, so let's say I want to generate 50 words, then check out what will happen. So things will start getting repeated. So you see this, to me today, the rows of, and so on and so forth. So why the heart, like that? So why does it happens? Because it's a probability which we are predicting. So the next word which you predict will be having the most probability. But if you predict something which is in a long sequence, then the probability will further drop down, and you will have very bad input. So uh, so what I have done, I have put less number of words as such in the output, which can be, and it is doing a better job with that. We can try something else as well. So for example, it's like how Indian musicians, they create the rap music. You just put some sentences, it creates the rhyming words, and then you have to sort of little arrange it. And one thing which doesn't do till now is punctuation. No, there will be no full stops and so on and so forth. So my love, my daughter, it's I let's say my love, my life, and so on and so forth. Let's see what happens, and then so on and so forth. So this is something using those type of sequences. I have created this much of poem till now. So sailors sail the sea of the land, ups and downs in the wave of the sea. I think we can put it one full stop here. Way from the precious love of life and the rose of Tranley, left my wife and the land and the mountains. I think we can put a maybe in the mountains, land or the mountains, and so on and so forth. Farewell of the gold and love to the town of the bridge of today, and so on and so forth. So this on a overall sense, how this is how we create rhyming poetry with Azure machine learning, with RNN, with LSTM as such, and how do we create one end-to-end solution. To further improve this, you can get a bigger data set. Data sets are available. All the poetry these days is open source. You can further get a little bigger data set and run it for more epochs, and definitely try the maximum sentences as well. Try the maximum how clean your data is, and try to improve it.